So today we're going to look at solubility in biological systems. Lots to talk about with respect to that. So basically, solubility refers generally to a solid in a liquid, and there's a KSP. It's basically the equilibrium constant between a solid and its constituent ions in solution. And so it looks very similar to our traditional equilibrium constants. And so here's basically the equation. Here's your KSP. And so the MCAT probably give you some problems where you have to use that. We'll see one of those in a minute. Solubility shouldn't be confused with miscibility. Solubility is a more general concept. It usually applies to a solid being dissolved in a liquid. Miscibility is usually with two liquids. So if you're 100% completely miscible, then you'll have two compounds that are 100% dissolved in the solution. Here you see cyclohexane and diethylamine in carbon tetrachloride, and they both are miscible in this solution. Cyclohexane is clearly more polar because it's just carbons and hydrogens. Here you see the nitrogen and diethylamine. But if you actually add a solution of 10% hydrochloric acid, what you can do is generate an aqueous layer and a nonpolar layer. And by protonating this amine at low pH, what you can do is create the charge, and that drives it in to water. So we can actually separate based upon that. And there's a Ki over here is basically the concentration of a species in the organic layer divided by its concentration in the water layer. So here's the idea of a KSP problem, as I mentioned earlier. So this is calculate the approximate concentration of lithium ions when lithium phosphate reaches its molar solubility. Look at its KSP is 2.7 times 10 to the minus 9. So it's not very soluble. Notice that it says 25 degrees, and these KSPs, the solubility of something, is definitely a function of temperature. You probably heated up solutions in order to get things to dissolve faster. So what do? We know phosphate has a -3 charge. We write out our equation here. We set up our KSP, and what we end up doing is we know the value of the KSP. So we set up the algebraic equation. We get 2.7 times 10 to the minus 9 equals 27x to the 4th power. We plug and chug, and ultimately what we calculate is that the concentrations of lithium is 1.0 times 10 to the minus 2 at its molar solubility. So the AAMC MCAT lists something called the common ion effect, and this is basically going to be solubility meets Le Chatelier's principle. So here what we have is calcium chloride dissolving in an aqueous solution to calcium plus chloride ions. But what happens if we actually throw in some sodium chloride into that beaker there? So what's going to happen? Well, if you notice that what's in common is chloride from sodium chloride and chloride from calcium chloride. And so what's going to happen then is Le Chatelier's principle is going to push this equation to the left, which is going to favor the actual calcium chloride parental molecule. And so the common ion effect always leads to a decrease in solubility through Le Chatelier's principle. As you see here, by going to the left, you form more calcium chloride that is not dissociated. So there's a whole bunch of solubility rules. I'm just going to point out a few of them for you. You should probably memorize these in more detail. So there's group 1 salts like sodium, potassium, lithium. Those are pretty soluble. Nitrates are soluble. Salts containing chloride, iodine, bromide are generally soluble, but silver salts are not very soluble. And calcium phosphate's interesting because it's pretty insoluble. And what that does, it sets up the parathyroid hormone. And we always have to think about biology when we think about solubility. I'm going to show you some more examples about the problems that cells have with transporting fats and other non-polar molecules. So calcium phosphate's KSP is 10 to the minus 33. That's very insoluble. And so you probably know what the parathyroid hormone is. It works in antagonism to calcitonin. And the parathyroid hormone, PTH, is known as a phosphate trashing hormone. So what does it do? Well, it actually prevents the kidney tubule from reabsorbing phosphate. And by doing that, what you do is you actually waste phosphate in the urine. So what's happening is that you're retaining calcium, but you're kicking out phosphate because you don't really want a lot of calcium together with phosphate. What that's going to do is it's so insoluble, it's going to calcify tissues, which is a big problem. So what that does, it sets up our capacity to look at a question like this and answer it, which the following graph describes the relationship between serum levels of phosphate and ionized calcium. You take a look at that, we know they're inversely related. So it's looking like this is the best one here. The higher the calcium we have over here, the less phosphate we're going to have. So we've talked about the hydrophobic effect before. This explains using thermodynamics of entropy and order why it is that like dissolves like. And so I've mentioned this before in the context of bioenergetics. We've seen this in the context when we talk about membranes and lipids. And so what you have over on the right here is the orderly water molecules surrounding these two phenylalanine residues here. So it's more ordered, there's less entropy. But if we add a little bit of salt into the solution here, what happens is that the water molecules will get displaced because they want to basically form complexes they want to solvate the sodium. And by doing that, we create a more entropic situation here because we've disordered the orderly water molecules in the absence of the sodium. So in the presence of sodium, you create more disorder. And as a consequence, what happens is that these hydrophobic residues can come together and interact with each other. And this, of course, explains why it is that hydrophobic residues are internal inside of protein structures, the hydrophobic effect. So Henry's law is about the solubility of gases in solution. It's very simple, straightforward. It's the amount of gas dissolved in a liquid is directly proportional to its partial pressure above the liquid. There's S equals Kp. We have the solubility of gas, the pressure, and you also have Henry's constant. And there's this concept of effervescence where you escape, a gas escapes from liquid. This explains what happens when you open up a soda pop can or bottle. You see the fizz. That fizz is effervescence. And what's happening is when you open it up, you actually have atmospheric pressure. And since the pressure inside the can was higher, then you're going to bubble out until like Henry's law. So this could be applied to free-floating drug delivery. This is pretty interesting here. So we're going to take our knowledge of effervescence and apply it to buoyancy in a physical sciences problem. So this is a drug delivery mechanism. Over here on the right, you have the stomach. And one of the problems with oral medications is that the pills transit through the stomach pretty fast. And so you don't get proper absorption. This is particularly true when you have a compound, a drug that has a low solubility at high pH values common to the intestines. You may want it to absorb in the stomach because it's a more acidic environment, or you may want to deliver the actual drug to the stomach itself. Maybe it's something like a proton pump inhibitor or some other medication for ulcers, etc. So what people have done is they've created these microparticles here. And what you have is on the outside, you have a swellable membrane layer. So this is basically a polymer that can absorb water and swell up. And then you have an effervescent layer. And this is a chemical that when it reacts with stomach acid, protons like carbonate will create CO2. And the CO2 is a gas, obviously. And what happens is then as the water comes in and you create CO2, what you do is you expand the volume and you start to move up because this is basically the buoyant force. And then you can actually sit at the surface here because the density of the particle will be lower than the density of the gastric juices, which is about 1. And then the drug gets released over time. And so as the stomach empties from the bottom, you're always sitting at the top. And what you can do is have your drug active in the stomach for much longer times using the principle of effervescence. So another way to deliver molecules that are difficult, like hydrophobic nonpolar molecules, is through micelles. And so micelles form when you have polar head groups in hydrophobic tails. They form these structures here where the actual polar head groups are on the outside, but inside it's very nonpolar. Now, phospholipid bilayers, they form bilayers, they don't form micelles. So it's a specific property of phospholipids to form the bilayer, but other lipids form micelles. And what you see down here is that you have these nonpolar groups with the polar heads. They're just floating around in solution until they hit a critical micellar concentration called the CMC. And then what they do is they form their micelles. And so what happens then is that we can use micelles that are formed in the GI tract to actually deliver molecules to their site. And one of them is the transport of vitamin A or its precursors like beta carotene. So, you know, beta carotene is high in carrots. It's actually a provitamin. It's a precursor to vitamin A. And so what happens then is that you transport this incredibly hydrophobic molecule. You should probably appreciate that it's composed of terpenes, which are 5-carbon isoprenoid groups. That's on the AAMC MCAT content outline 2. And so basically beta carotene through a micelle will actually get delivered into the intestinal cell. If you notice, what happens is that it gets converted into retinal, which is the aldehyde, oxidized to the retinol, which is the alcohol, then esterified, and then transferred in chylomicrons. We've seen chylomicrons before. These are lipoprotein particles that are used to transport exogenous fats consumed in our diets, but also things like non-polar vitamins or water-insoluble vitamins, D, A, K, and E as well. We take it to the liver where it's stored. And then when you want to deliver vitamin A to peripheral target tissues, what you need to do is have a binding protein here. So all these hydrophobic things need to piggyback onto something else. They need to be on a chylomicron. They need to be on a retinol binding protein in order to get delivered. Otherwise, they're so insoluble, this like drop like a rock in your blood vessels here. Now, bile salts is another important thing that uses micelles as well. So we know that bile is derived from cholesterol, made in the liver, stored in the gallbladder. And you don't see the gallbladder here, but it's kicked out during in the GI tract during digestion. And so bile is going to be used in a moment to actually emulsify fats, but it can get excreted. It could also get recycled back through sodium symporters. And what happens with bile is that it forms micelles. So here's a really interesting micelle. This one contains vitamin K as writing. This actually has, looks like cholesterol here. Here's basically a fatty acid that's been esterified to glycerol here. We see bile salts. These are conjugated. Over here, you see some groups over here that looks like it's been on a cholesterol derivative. So bile salts, what they do is they emulsify fats and they provide the surface area for pancreatic enzymes to actually start working on these molecules. Those could be lipases or et cetera. So we'll take a look at solubility and jaundice as well. This is a big problem in clinical medicine. So we talk about red blood cells and hemoglobin. We're constantly thinking about delivering oxygen to peripheral tissues. And that's great for hemoglobin and its function. But what happens when hemoglobin gets old? You have to degrade it. So the way you degrade it is you break it down into heme and globin, but the heme actually is composed of the iron as well as the pyrrole groups. And so what you can do is break it down into bilirubin here. And there's an enzyme called glucouronyl transferase that actually makes bilirubin diglucuronate. It's kind of a complicated word, but you basically put sugar residues on it. So when you put sugar residues on the bilirubin, what you do is you generate all these hydroxyls and a carboxyl group over here. What you're doing is you're making the molecule more polar by adding OH groups. They get hydrogen bond. It's more polar, it's therefore more soluble. Bilirubin is insoluble. In order to get it kicked out for excretion by the kidneys, you have to add these sugar groups here, so you need this enzyme expressed. The problem, though, is that there's many circumstances where this enzyme is not expressed. One of them, the most common one, is in newborn babies, because neonates don't express this enzyme until almost actual 40 weeks into pregnancy, right around normal childbirth timing. But it turns out that if you're a premature baby, for a variety of reasons, you may not have an adequate level of the enzyme expressed. As a consequence, what happens is that you can't modify your bilirubin to make the diglucurionates. And as a consequence, bilirubin builds up and you get what's known as jaundice. So what docs have figured out is that if they take those babies that have jaundice and they stick them under a UV lamp, what happens is that the energy from the UV lamp. And we know, since there's all these double bonds over here and that UV reacts with double bonds, what you do is you create an isomer called photorubin, which turns into lumorubin. And it turns out this is more soluble than bilirubin, and you can actually get rid of this product here. It won't build up and create jaundice. And so that gives you some time. And by the time you've gotten rid of all this, the baby can now mature and express this particular enzyme. So lastly, look at uric acid and gout. Gout is a really big deal. It's common in males more than females. It's known as businessman's disease because the businessman goes out for a steak dinner and drinks alcohol. And what does the steak dinner have? It has a lot of purines. And what does the alcohol do? It dehydrates you and it concentrates things in your blood. So let's take a look at the pathway. So purines turn into hypoxanthine, which is a purine, and it gives a xanthine. Ultimately, we make uric acid, and it comes into a salt known as monosodium urate. Now, when this builds up to a not very high level, you actually saturate, you have hyperuricemia, okay? And if your pH is low, what these crystals form in a lot of places, particularly your toe area here, it's called podagra here. This is incredibly painful. This is a giant inflamed joint, and some of these people can barely walk. And so some of the conditions that people use to actually get rid of gout is to abstain from alcohol and meat, but also you can take some therapeutic drugs that actually inhibit aspects of this pathway here. So what you can think about is that most cases of gout develop in the extremities, like the toes. Why there? And the reason why is because that's probably the coolest part of your body because it's so far away from your heart. And so we know that solubility is a function of temperature. So the further you're away, the more extreme position you are, the more likely you're going to get the monosodium urate crystals to actually form. So we have gout, and then we're going to do some passages that are going to test our knowledge of solubility. We're going to apply our general organic and biochemical knowledge to actually relevant clinical medical conditions that are important for the MCAT as well as for med school. So we're looking at bile salts and gallstones, medical marijuana, and glaucoma. You should recognize that marijuana's component THC is very nonpolar. So it has all kinds of problems. And then there's uric acid and gout. And so let's do the workshop passages.